suppose you want to say something like, for example, I want the people downstairs to help me out by telling me if, for example, they're not seeing something or, you know, something is wrong, then they may need to speak. So you can turn on your mic and speak to me, but only while you're speaking to me, right? But always keep off the sound. Always keep off the sound. Otherwise, we're gonna get echoes. All right, let me share this. Let me share the screen. Okay, so we started to look at the hyperparameters, and remember, there are two types of parameters. There's what we call parameters, and then there's hyperparameters, right? Now, the parameters are what the model learns. There's another term for the parameters. It also starts with W. Weights, right? Weights is the term weight loosely means weights and biases. So W plus B, right? Remember, and I tell people this all the time. Every super complicated thing comes down to a set of tiny things that are put together in a certain way, right? W plus B. This is all a neural network is, right? It's W plus B. That's all it is, W and B, right? Because it's thousands of linear regressions. And all you learn in a linear regression is W and B. That's it. In the case of a neural network, we're learning thousands of interconnected we're learning thousands of interconnected W's and B's, right? Right? And so when we say weights, we loosely mean that B is a weight as well, right? But it's just the weight of the line. So take, for example, you have a neural network, right? And you have, you have some neurons. And, so you have these neurons, right? Right? In the first layer, right? And you have neurons in the second layer, right? All right, let's do a 3-3, right? That's fine. And you're gonna have linear regressions in between them, yeah? Right? Right? And you do this a couple times. So all of these are simply linear regressions between the neurons, right? And in the first layer, you learn things like edges. And in the second layer, you learn things like shapes. And in the third layer, you learn things like features and this type of stuff, right? Now, let's leave it at this, right? And so all it really is, it's like you're saying, okay, you have these different weights, right? And you can think of it this way. It's like some lines are thicker than others, right? Some lines are thicker than others, right? Right? You can think of it that way. You have a weight of each line has a weight, right? Now, etc., right? Etc., etc. And then you can think of it like there's a B connected with each of these neurons, right? Remember, each neuron has a B connected to it, which is the bias, right? Okay, let's do one thing. Let's plug this in real quick. All right, so these parameters that we're learning, the W and the B, so each of these neurons has its own B, and then each line has a W, yeah? So we're learning these weights and biases that represent the knowledge inside of the neural network, right? When we train the neural network, this is what it's learning, right? This is different from the hyperparameters, which we control. You, the data scientist, you, the person who is tuning the model, right? Controls the hyperparameters. And we started to look at some hyperparameters, right? On, well, week 4. Well, last week we started to look at some hyperparameters. Yeah. We saw a bunch of different. We saw a bunch of different hyperparameters, like let's see if we can find this PowerPoint here. All right. All right, yeah. So we found some, so we talked about some hyperparameters, right? And the first thing we talked about was the image size. Yeah. First thing we talked about was the image size. And we said that CIFAR, for example, has 32 by 32. Yeah, it's coming in with 32 by 32. Now, one of the things you can do, for example, is now if you're using your own company's training data, or if you're using your own project's training data, right? If you have, so the thing to understand about CIFAR is that it's pre-processed, right? The reality of deep learning, machine learning, AI, right? All these fields is that pre-processing the data is actually, can take somewhere between 50% to 80% of the actual time it takes to develop your network, right? So getting the images into the same size, scaling them down, right? So they have to be the same size, must be the same size. You might have some images that are 800 by 600, some that are 500 by 300, etc., etc. So they must all scale to the same size. That's the first thing. And of course, you could upscale or you could downscale. Upscale meaning increase the resolution, but there's no point in increasing the resolution of a picture. So for example, CIFAR, you could take it and you could make it 64 by 64, right? There are some sort of artificial techniques that you could use to, take for example, you're showing a 1080p picture on a 4K screen. There are some techniques that you can use to artificially upscale the resolution. But there's no point in that because the information has already been lost. Thing to always remember, when you move the resolution from a higher resolution to a lower resolution, you're losing information. Yeah? You're losing information. Yeah? So there's no point in upscaling. Typically what you're doing is you're downscaling the resolution, right? All right. So must be the same size. Must be the same size. You may mess with the layers. You may make it black and white instead of color, right? You might reduce the number of colors. So for example, in this, all right, guys downstairs, please mute your microphone. Wait. All right, very good. Okay, good. Okay, so they must all come down to the same size, right? And there's tools you can use to do that, right? But the first thing is to make sure they're all the same size. Number of deep connected layers. So for example, here we have one hidden layer in this network. We have one hidden layer in this network, right? Remember, we start with model 1, and then we add a convolutional layer, right? 32 filters, 5x5, kernel, etc., etc. But in this case, what we're saying is that we have one dense layer, right? We could add a second, yeah? And we can also change the number of neurons that the layer, that the network is using, right? So we can change the number of layers. Remember, after each dense layer, you need an activation. You need an activation layer, right? Because remember, after you've learned, remember the equation, z equals wx plus b, right? We have z equals wx plus b. We're learning w and b, right? X is the input to the neuron. X is the input to the neuron. So X is this value going into the neuron, right? We're calculating Z equals WX plus B. Then we're saying activation is equal to G times Z, right? And in this case, we're using ReLU. So after every dense layer, we need an activation layer, right? That's very, very important. Very, very important. If we look at, let me show you another. Let me show you how this looks in PyTorch. Now, by the way, this is extremely important. I should have pointed out that this is TensorFlow that we're looking at. TensorFlow is a Python library that's used for deep learning. Probably the most famous Python library used for deep learning, right? If we look at the PyTorch version, PyTorch is another very important and very popular library used for deep learning. Take, for example, in PyTorch, what we have is we have instead, what we have is, okay, right, yeah. So we have linear 8192, yeah, it's the same as the dense layer, and then the ReLU, right? So we have the linear Z equals WX plus B being calculated here, and then we have the activation there, right? So after every linear or dense layer, we must have the activation. All right. Let's jump back over to here. No, the thing to understand, of course, is that this is going to make your network grow. So for example, let's run this. You guys can hardly see this, right? Is it a little bit better now? Sai Krishna, can you see it? Can you see the text? Okay, good. Excellent. All right. All right, very good. Very good. Cool, cool, cool. All right. All right, that's a prancing horse for sure. All right, good. So here our total parameters we're learning is 443,000. Like we said, this is why we need GPUs. If we add another dense layer, right? Let's add another dense layer and see what it looks like this time. Why is it taking so long? Oh, it's training that thing. This time we have 706,000, right? So the point is, as we add, oh, I had already added a dense layer. All right, so here we have one hidden layer. We're at 181. If we add another, then we go to 443, right? So more than double. And if we add another, remember, if you're going to add another dense, you have to add another activation. Yeah. Remember, the dense is where we're saying Z equals WX plus B, right? And the ReLU is where we're saying A equals G of Z. Cool? Here now, it goes up to 706,000, right? All right. Now, let's look at something. Let's look at something, by the way. Let's look at something. Let's run this. Let's do some training. Let's do some training. Let's train it with one hidden layer. Cool. Let's train it with one hidden layer and see what happens. All right, so each epoch, remember, an epoch is what? What does an epoch represent? Pass through of what? Through what? Of the network passes through the data, or the data passes through the network, right? All right, very cool. All right, so we're taking somewhere about we're taking about, it kind of varies. We're seeing somewhere between, let's look on the small side of it. Let's say 5-6 seconds, yeah, per epoch. This is what's happening, you know. Notice as we train it, the accuracy goes from 31% to 49, 54%, 57, 59, 61, 62, 64, right? Cool. Let's train it this time. Let's train it this time. All right, let's train it for 10 epochs. Let's train it for 10 epochs. Epochs equals, let's train it for 8. No, let's train it for 7 epochs, right? All right, so 11 seconds. Now, the first time that it puts the model on the GPU, it takes a few seconds to put the model inside the GPU, right? It has to take the model and pop it on the GPU. So that takes a few seconds. It's always going to take a couple extra seconds first time, right? All right. So 7 seconds, 10, 6, 5. It will fluctuate. It will fluctuate. But we're going to say it's taking between 5 and 7 seconds on the faster side, right? Okay. Now, let's capture all of this. And let's make this. We're going to make this. Actually, what we're going to do is, I'm going to make this be, What am I trying to do here? Trying to, okay, yeah, all right. Let's capture this, right? Let's capture it this way. Let's capture it this way. Oh, okay, good. All right, let's capture it this. And this is one layer, 512 neurons, right? Right? All right, very cool. Let's try something. Let's do this. Let's put in another dense layer. Remember, when we add dense, we have to add ReLU. Cool? All right, so we recreate the model. It's gone up to 7. Dense activation, dense activation, dense. All right, we added a layer. It was already at 400 and it was already at 400 and something, 443. So we added a layer. That's the point, right? Let's see the effect this time on the time and the accuracy. Now, okay, so here we have, it starts at 64% and it goes up to 69%, right? It goes up to 70%. That's the training accuracy. Note that the training accuracy is different from the validation accuracy. The training accuracy is the accuracy on the training set. It's learning on the data that we're training it on. This can easily approach 100%, right? But the validation accuracy may still lag. So this time we're at 12 seconds, 15 seconds, 11. We're hovering somewhere between 11 seconds and 12 seconds, right? For this run, because we've added a dense layer. We've added a dense layer, which means we're doing more what? More, well, activations, yes, but an activation is what? That's a general term for an activation. It starts with C. We're doing more computations or calculations, either one, same thing, right? So it's taking more time. Now, what's the effect on the accuracy though? We should be achieving greater accuracy at the start. In reality, we're not. We're going from 30 to 48 to 54 to 57. The accuracy is actually smaller, right? But actually, I made a mistake the first time. What I wanted to do was to go from 1 dense layer to 2. So let's do that. Dense, I'd actually wanted to go from 1 dense to 2. Wait, hold on. And am I missing a ReLU? Okay, let's rerun that again. I made a mistake. I wanted to go from one of these, 1 dense and 1 activation, to 2 dense and 2 activation. So let's run it this time, right? Let's run it again. Let's look at the training time and the training accuracy. Yeah. So 181 parameters, which means 181 calculations. Yeah. Fastest time is 5 seconds. All right, starts at 41%. Then Is the class downstairs hearing and seeing everything? Is the class downstairs hearing and seeing everything? All right, so 5 seconds, 5 to 6 seconds, right? And this is with one dense, one activation. All right, Bharat says yes, Dinesh says yes, right? So it was actually 2 layers, right? So let's capture this. Let's see what this looks like. Accuracy starts at 29, goes to 46, goes to 51, 54, 58, right? All right, let's capture this. All right. Right. Let's capture this. Now we're gonna add a second layer. Sorry, I messed up the experiment the first time. All right. All right, so we're gonna add a second layer. Gonna add a dense and an activation. Rebuild the network. This time we have 443,000 parameters, and we're gonna train the network again for the same 7 epochs. Let's see the difference this time. Let's delete this so there's no confusion, right? All right. Accuracy still starts at 29%. Goes to 49. Goes to 54. Goes to 57, right? Goes to 59, goes to 61, right? Goes to 64%. So we have a 6% increase in accuracy after 7 epochs, right? Still starts at 29%. It should have started higher. But one of the things you want to do sometimes is to run it several times. You want to run it several times because here's a problem. Depending on the weights that you start with. Depending on the weights that you start with, right? Remember, you start with these random set of weights. So for example, you have a 3x3 network, right? And you have a 3x3 network, right? 3x3, right? They have this 3x3 network, right? And you initialize the weights randomly at the start. Yeah. So for layer 1, right? You have layer 1 to layer 2, right? Right? And let me show you how it would kind of look. It would look kind of something like this. So you have neuron 1. So neuron 1, let's color this yellow, right? Neuron 2, let's color this green. And neuron 3, let's color this orange, right? Right? And so you have layer 1 neuron 1. You have a W for neuron 1, neuron 2, right? You have a W for neuron 1, neuron 3, right? You have a W for neuron 1, neuron 3, right? Let's do this again. Then you start it over again. You have a W for neuron 2, neuron 1, right? A W for neuron 2, neuron 2, right? Then you have a W for neuron 2, neuron 3, right? You have a W again for neuron 3, neuron 1, W for neuron 3, neuron 2, W for neuron 3, neuron 2, and a W for neuron 3, neuron 3. Everybody with me? So in other words, remember you have these. Remember you have these. Right? Sorry, I'm doing the wrong thing. Right? And you have right? And it's W1 neuron 1 is this line. W1 neuron 2 is this line. Yeah? W1 neuron 3 is this line. Everybody with me? Then you have let's make this line green. Right? Right? Etc. Etc. Right? And we're going to make this orange. So we have 9 weights. We start with these 9 weights, right? Cool. We start with these 9 weights. All right. Now, depending on, these are randomly initialized, but you can control the initialization by setting what's called the seed. Yeah, we'll look at setting the seed. But the point is, you can set the seed in order to initialize the weights with the same values each time. And that will start off the training at the same place. All right. But the point is, if we rerun this, let's rerun this. And we started at 29, ended up at 64. Wait, actually, let's one time. Let's rerun everything. All right. Make sure we're starting off at the same with the same conditions, right? Do that. Already satisfied doing that. Load that, load that, load that, display that, right? All right, we have our 443,000 parameters, right? And we're now fitting the model. Notice, by the way, so all of this is the optimizer parameters, right? Hyperparameters that we talked about. Notice the syntax. We have the model one. We built our model one here, right? Model one equals sequential. In other words, sequential just means several layers. We're going to add several layers. And each of these is one layer that we're adding, right? And then we say model one dot fit. This is the general terminology used in AI, machine learning, data science, right? We say we fit the model to the data, right? The data is the reality. The model is what we're fitting. We're fitting the model to the data. It's like when you go to no, India is extremely interesting. India is extremely interesting because you have saris, right? It's no, it's this is super interesting to me, you know, right? How culture how culture affects everything. So you have this very large population, right? You have this very large population. And so what do you do to make sure that you have enough clothes for everybody? You have the sari. And the sari is kind of a one size fits all, isn't it? Pretty much. You have different size saris though, I notice. I know you have different size saris. But you can lend your sister your sari very easily. Am I right or am I wrong? Am I right or wrong? Super, super easy, right? Right? So the point is you can, you can exchange clothes very, very easily. You can reuse clothes. You can pass on clothes very, very easily. And by the way, in Jamaica, I mean, and in Western cultures, we have our, own share of, sharing clothes, right? I'm not saying we don't share clothes in the West as well. But the point is that, it's very interesting when you look at culture shapes, how culture shapes everything. How culture shapes everything. All right, very cool. Okay, very cool. Okay, so yeah, so we start at 29, we end up at 63. Yeah. So still consistent, 29 to 63. We got a 5 to 6% increase in the accuracy. Let's drop it back down to the one activation, one dense, right? Let's run it again. And let's see if we go back, right? So the point is, with more layers, you get higher accuracy. It's kind of the whole point of this. But it takes more time. But it takes more time. So is it running something down here? Yeah, so let's rebuild this with one dense, one activation, right? And let's fit the model again, right? Wait. Rebuild the model, and then we're gonna fit the model again. All right, very good. Here we go again, right? And we should drop back to 29 and 58%. Yeah. And it should also run faster. First time we put the model on the GPU, it takes a little time to place the model on the GPU. So it takes a couple extra seconds, right? But okay. We're at 28%, and it grows to 45 to 49 to 53. Goes to 56. Well, yeah, 55, 56. It's gonna go to 56.68. And after 7 epochs, we're back to 58%. So fairly consistent. We gained that extra 6% accuracy by increasing the number of layers, right? Now, let's do another experiment. Let's do another experiment. And this time, let us instead of increasing the number of layers, let's drop this to 256 neurons, right? Fastest time was 6 seconds. Yeah. Let's see what the fastest time will be if we reduce the number of neurons to 256, right? 256 neurons, we're down to 104,000 parameters. Yeah. Let's fit the model. Let's see how fast it fits and what kind of accuracy we're going to get instead. All right, so remember, 29 to 58. 29 to 58, right? I mean, not much faster, not much faster in reality. Not much faster, right? It's still somewhere between 5 and 6 seconds. So we haven't sped it up at all, right? We really have not sped it up. But what's the accuracy like? This time we're going from 26% to 56%. Again, not much less. Let's do another experiment. Let's drop it again. Let's drop it to 64 neurons. Yeah. All right, let's fit our model again. Let's see what kind of times we get. "12 seconds still takes time to put the model on the GPU. Starts at 23% this time. It grows to 39%. And it goes up to 44, goes to 45, well, 46. 49% about, 50%. Accuracy drops to 51%, yeah? So by reducing the neurons, theoretically, it was supposed to run faster, right? But it didn't, right? Now, there's an overhead to everything. There's an overhead to the whole process, yeah? And so you're really gonna see the difference with bigger networks and bigger pictures, right? You may not see it with these, with this. In other words, it's gonna take a couple seconds just to do the tidying up, just to do the final calculations, etc., etc. So when it's a few seconds, you may not see the difference. But okay, we have accuracy going from 22% to 52% this time, right? Let's drop it even more. Let's drop it to, let's do something ridiculous. Let's use 8 neurons. We have 8 neurons. Let's fit the network again. Model 1.fit. Let's see the time it takes. By the way, we've dropped to 30,000 parameters, right? So we're way down from 180 to 30,000. It's still taking 12 seconds to fit it onto the GPU. Still taking a couple seconds to run it. Wow, 15 seconds this time. That's interesting. That's fascinating. But notice the accuracy goes from 14%, goes to 24, right? Goes to 25. Goes to 26. The time is still around 5 seconds, right? We're still not speeding it up too much. It tops out at 27%. You see that? So our accuracy tops out at 27%. There's an optimal number of neurons in this thing. Let's try a ridiculously large number of neurons. Let's try 8192, right? Notice we typically go in powers of 2. Powers of 2. So 8192, I think, is 2 to the 14. Yeah? 2 to the 14, right? 2 to the 14 equals, no, 2 to the 13 is 8192. Yeah. All right. So let's try this. We have 8192 densely neurons in the dense layer this time. We have 2.5 million parameters, right? And let's try to fit our network. Let's see what the difference is with the accuracy. Just now we topped out at, what was it, 28%? 29%? Bala, what did we top out at just now? All right, we have to, you guys are not sure, so I have to double check it. 8, right? So 16% starts at 16. Now, with all of this, by the way, you do want to record what's happening. Yeah? So you want to have your little spreadsheet and you want to see what's going on, because we're doing what's called a grid search. So for example, we have layers 1, neurons 8 time let's call it 6 seconds. So no difference in time. Accuracy goes from accuracy start, accuracy finish, right? So it goes from 16 to 31, right? This time, let's do something ridiculous, right? All right. Let's put in 8192. Let's see what happens. Now, understand something. Putting in 1,000,000 neurons is not going to increase the accuracy to 100%, right? There's an optimal number of neurons, yeah? There's an optimal number of neurons. There's an optimal number of neurons. And once you pass that optimal number, you may actually start to decrease the accuracy, right? Because sometimes you're starting to learn features that don't exist, right? But the point is that with 8,192 neurons, this time we're starting with the 8192. Time is still 6 seconds, right? Started accuracy is 33, and the ending accuracy is going to be 64, right? $64, right? Teaching with this Zoom thing is a pain sometimes, right? Notice we don't have that much. So the number of neurons definitely makes a big difference, right, to the accuracy. But notice that it's not that much different from, say, 1,000 neurons, right? So 2.5 million parameters. Let's drop it back down to 1024 neurons, right? Let's fit the model again and see. So we have 1024, right? That's 2 to the 10 power, 2 to the power of 10, right? The time per epoch is still around 6 seconds, right? Now, one of the reasons why, for example, the time doesn't change is because we're fitting a network that is minuscule compared to the power of the GPU that we're running this on. We're running this on an A100 GPU on Google Colab, right? It's a drop in the bucket. The amount of time per epoch doesn't start to change until you start to properly test the GPU, right? So see, accuracy starts at 30.5. Let's call it 31. All right, let's call it 30. And it goes to 61. See? So there's kind of an optimal number of neurons. And if we go back to 512, etc., etc. All right, you get the point. You get the point. You get the point. Let's try this. All right, so let's try doing something different. Let's try tuning the convolutional layer, right? Let's try a different kernel size. Yeah. Now, one of the things when you're tuning is you want to try one thing at a time. You're going to try one thing at a time. Yeah. You try one thing at a time and you make a note of what it did, right? When you're very experienced, you can try several things at a time. Like you can change the convolution layer and the dense layer, right? But that's after you have a lot of experience. When you have a lot of, it's like, for example, when you're cooking biryani, you can say, all right, I cooked some mutton biryani last night. It didn't come out quite the way I wanted. Here's what I'm going to do this time. I'm going to add a little salt and see how different it tastes. So 1 week, you add more salt or you add less salt. You get the salt right. The next week, you tune the spices. So for example, what's the main spice in biryani? What's the main spice in biryani? Chili? Which spice do you use in biryani? Huh?
Cinnamon.
Somebody's downstairs is saying what? Shankar, you're saying what?
Cinnamon.
Cinnamon. Oh, it took somebody from downstairs. You people upstairs can't cook. All right. So the next week, after you've gotten the salt right, then you start to mess with the cinnamon. And you vary the cinnamon up and down until you get it quite the way you want, right? Then the next week, you change the cooking time, right? Now, when you're a chef and you've been doing this for a long time, then you can change 3 things at the same time and see what the effect is, right? And in your mind, you're sort of triangulating the effect on each on the biryani, right? But when you're just starting out, you want to change one thing at a time, see how it changes, how it affects the model, and then tune the next thing. But anyway, let's try a different, okay, so by the way, we need to note down what we have at this point, right? So we have one layer, 24 neurons, And then we're gonna say the convolutions kernel is 3 by 3, right? What was it? 5 by 5, right? This time we're gonna try a 4 by 4. So this should learn more detailed features, right? Wait, oops. This, all right. All right, now notice 5 by 5, we have 334,000. Okay, yeah, so the parameters don't change. And then we go 4 by 4, all right? Let's see how that affects the accuracy of the model. Let's fit the model. Starts at 31%. Goes to 48. So remember, with smaller kernels, we're learning more detailed features, right? With larger kernels, we're learning larger details. Yeah? Yeah? Or less details in reality. All right. We reduce the kernel size from 5 by 5 to 4 by 4. And after 7 epochs, we've gone from 31% to same 61%, right? Let's try 6 by 6 and see what the effect is. Six by 6. Let's fit the model again. Six by 6. Same parameters. Oh, we haven't really been checking the time. Let's forget the time for a second. One layer, 1024. Let's see what is start at accuracy of 29. And the accuracy we finish with is going to be still end up with 61, right? Oh, why? Oh, 59. Oh, that's interesting. 59. Why did I think 61? Okay, so 59. Okay. Let's make it even bigger. So we should be learning even less details. Let's see what it does with our model. Then we have 7 by 7. Same one layer, 1024 neurons. That dense, we started at 30%. Now remember, very importantly, you really have to run these epochs a couple of times to really see the true effect. Because remember, depending on the way remember the weights are initialized randomly at the start. Yeah, and depending on how the weights are initialized, depending on where the weights start, it may end up start and end differently. Yeah, especially the start. And this time we still get 30 and we end up at 58.5. So we're actually getting worse. Let's try 2 by 2. Let's go the opposite way. Let's try a 2 by 2 kernel. Right? Let's see what it does. Fit that. Right? And let's fit it and see what it does. right? And like I said, you want to write down what you're doing so you see what the effect is. You can see whether you're going in the right direction or the wrong direction. We start at 31%, right? Right? We're not really, let's hide the time because we're not really noting the time at this point. 31% goes up to 59% there. And after 7 epochs, it goes to, still goes to 60%. So not much difference, right? But yeah. All right. People, I'm gonna call it that for today. I have to run to the restroom. I have to run face my dentist. All right. Hold on. I'm running. Let's see who's here today. All right, people downstairs, I'll be coming to take attendance, but if your name is marked yet downstairs, you're late. But I'll be coming down there in a second. All right, let's see who is here upstairs. All right, who came in after I called attendance? Shafi. Oh, so I got you in there, Shafi. What? Oh, you came in while I was calling.
Yeah.
Are you sure? Is it? Oh, Vivek. Vivek, you're late. No? Why are you not late? Hold it. People, next week I'm marking people late. Next week, you're half a second late, you're late. Tell me one more time. Did I get your... Oh. Oh, Satya. Satya, next week you're late. Quarter second late. And you're late, right? Who else? Who else? Who else? Who else? Who else? Tell me. Ramakrishna, right? And who else? Ravi. Ravi Krishna. Ravi? R-A-V-I?
Yeah, IAVI.
Oh, okay. All right, got you. All right, who else? Everybody else is marked? All right, people, I want to show you all right, this whole thing happened in less than 10 seconds. You know how much he won by? He won by 0.1 second. Right? 0.1 second can make a world of difference. Now, we're not sprinters. We're not sprinters in here. Right? But what I'm saying is this. Don't say you're just only late by 2 minutes. Or all right, if you're bidding on a contract, let's say you have a tender. Anybody ever, you know about government tenders? Tenders. Tenders is where you submit a contract. Like you have a company or government and they say, we need some work done. I want you to bid for this contract. And they have a deadline for the tender date. And if you submit it 1 second late, doesn't count. All right. See you guys next week. I'm gonna go downstairs, take some attendance. Hi. Walk with me. I like yours more. You have a nicer shirt. It's true. It's true.
ఇది ఫెయిల్ అయ్యాక